So let's look at multiplication and division. Well, when multiplying or dividing, we're going to add the relative errors, or also known as that percent error, right? And then convert it back into absolute uncertainty. Remember that absolute uncertainty looks like this. Percent uncertainty is a percentage, the percentage of the uncertainty divided by the actual value. So the multiplying or dividing by a pure number, that is a scalar value, right, for those in linear algebra. So the 3 is multiplied by here and multiplied by here, just carried through. This means that 3 doesn't have an uncertainty with it, so we just take that and we end up with 36.9 plus or minus 0.03. It's not always that easy, but we'll go with that. The average, you get this a lot when you find an average, because if your uncertainty is 0.1 and you took 3 measurements, well, you're going to add 0.1, all of those together. But when we take the average of that, we have to divide it by those 3 measurements. So we end up with 0.1, right? So very often when you find the average of the uncertainty, it ends up being the actual uncertainty that you started with. That's very, very frequent. So just stick that back in your head. So now we'll move on to something a little more complicated. We'll calculate the density of sodium chloride sample with a mass of 5 plus or minus 0.01 and a volume of 2.3 plus or minus 0.1. Well, the density is mass divided by volume. So let's calculate the true value first, right? The actual quantity. That's going to be mass divided by volume, so 5 divided by 2.3, and that gives us 2.2. Roundabouts, 2.2. So now that's close enough, and that gets us there. Now we have to propagate this uncertainty right here. So what I'm going to do is I'm going to find the relative uncertainties or the percent uncertainties of each one. I'm going to add the 2% uncertainties, and then I'm going to stick that back into here. So watch me do it. I'm going to take 0.1 divided by 5, and then that is going to be multiplied by 100, and that's going to be 0.2. And then I'm going to take 0.1 divided by 2.3, that one right there, multiplied by 100. And that's going to be 4.35. Okay, the sig figs here aren't going to matter too much. And I'm not going to round right away, so I'm going to add these two numbers. Okay, so I'm going to take these two numbers, I'm going to add them. So I'm going to take 4.35 plus 0.2. And I get 4.55. Easy enough. I needed a calculator for that. I'm silly. So I'll take that, and this is my percent uncertainty. So I'm going to multiply this percent uncertainty by that, and then have to divide by 100. So I'm going to take 4.55 and then times 2.2, and then I'm going to divide by 100, and I get that. So 2.2 times 4.55, and then divide that by my 100 because I have to get it back into normal uncertainty, and I get 0.1. And that's plus or minus 0.1. So my final answer is going to be 2.2 plus or minus 0.1 grams per centimeter cube. Now, there is an easier way to do it. That was the long way, and that one's all broken down. But let me show you the easier way. So for calculating the rectangle, the area of the rectangle with the sides of So our rectangle is like this, and it's going to be 4.8 right here, and then 13.7 here. We're going to take our true value first, 4.8 times 13.7, and that's going to give us 65.76. So now that is the value, right? Now what I'm going to do is I'm going to take this uncertainty now, and I'm going to take the percent uncertainties, 4.8, and I'm just going to add these instead. Instead of that multiply by 100 and all that junk, I'm just going to add the percent uncertainties just like this instead. That makes it a little bit easier and less writing. And then I'm going to multiply it by that value that I have. So this is how I calculate that uncertainty. So that's why you calculate the value first. You'll take your percent uncertainties, add them together, and then multiply that whole term by your actual value, and then that will give you going to be 1.85. Now, like I said before, this value the uncertainty should only have one sig fig, so I'll just round it to 2. And this original value now should actually only have 2 sig figs. So I'll just take 66 plus or minus 2. And then that's unit is going to be centimeters squared. Okay, so you have to stay on your toes when you do these things. And so now we have this one, meters per second, kind of like a velocity thing. Let's do our value again, divided by 2.1. That's going to be 20.96, not rounding yet. And then I'll take my uncertainties, 0.05, divided by 44.01, add it to 0.05, divided by 2.1, multiply all of those by my value, and I will end up with 0.52, round it to 0.5. So let's round this one to its 2 sig figs. So that's going to be 21. So that's going to be 21 plus or minus 0.5 meters per second. All right, we end up with a little discrepancy here. Some people think that because this one has a decimal place and then this one doesn't, you should change this one to plus or minus 1 or change this to 21.0. It doesn't happen a lot. Sometimes it happens in this kind of situation. It doesn't make that big a difference, and it won't hurt your score. You won't run into it on the IB test. Okay. By the way, this is only worth 1 point, so nobody panic. And then this last one, we'll take this value times this value, 5.456 times 27.8. And then that will give us 151.6768, not rounding yet. And then we'll take 0.001 divided by 5.456 plus 0.2 divided by 27.8, all multiplied by that original value. And that will give us our value of 1.119. Let's round that to 1 sig fig. So that's going to be 1. All right. Let's round our original 1 to 3 sig figs. That's the least number. So we're going to round it to 152. All right. So we have 152 plus or minus 1. See how that works? And that's going to be grams times degrees Celsius. All right. That's how you propagate uncertainty for multiplication and division. Have a great day.